Okay, yeah. So hello everyone, welcome to the fourth talk of the Cosmic Voyages talk series. Today with us we have Dr. Prerna Rana, a postdoctoral research at the Department of Astronomy and Astrophysics at Tata Institute of Fundamental Research, Mumbai. She works on classical, special, and general relativity, pulsar astronomy, gravitational wave emission from supermassive black holes and black hole binary system. And she's also a member of the Indian Pulsar Timing Array, recently made the news for the ultra low frequency gravitational wave detection. Uh, so uh, Over to you, Dr. Prerna.
Thank you. So I'm audible, right?
Yes, you're audible.
Okay. Thank you, and very good evening, everyone. So that was a very kind introduction. As you know, I work at TIFR, and along with the Indo-Japanese collaboration Indian Pulsar Timing Array, I'm also working with another collaboration called the International Pulsar Timing Array, and I will be talking about that in my talk. So my talk is basically motivated by recent news which came on June 19th, and there were various news articles which you might have gone through. But you might be wondering that gravitational wave observatory which are there on Earth, like LIGO-Virgo-KAGRA, they are already discovering many gravitational wave events since 2015. As we know, the first detection happened in 2015. Now, what is this? All this excitement is really about. We have already seen gravitational waves. So, what is new? To say in short and in a fancy way, it looks like the entire fabric of our universe is humming with certain low frequency gravitational waves. And my whole talk is around this, trying to explain what this really means. So that's keeping this as a motivation in my mind. I have outlined my talk. First, I'll briefly discuss about gravitational waves and how gravitational waves now are extending to a multi-frequency spectrum. I will talk about pulsar timing arrays, which were recently in news. And as I very closely work with the Indian Pulsar Timing Array, I am going to talk about their first data release that we made last year. And I will also briefly talk about the upcoming second data release that Indian Pulsar Timing Array is going to make. And then I will talk, after giving all this background about pulsar timing arrays, etc., I will talk about the emerging evidence of gravitational wave background, which was in news. And finally, I will talk about International Pulsar Timing Array and how and why this is extremely important for gravitational wave background and other low frequency gravitational wave detection. So speaking about gravitational waves, at popular science level, you might have heard that these are ripples in space-time caused by some of the most violent and energetic processes that happens in our universe. But to understand or to physically understand what it really means, just imagine that there are a ring of particles just stick to the screen of my computer, and there's a gravitational wave passing through the screen of my computer. What this gravitational wave is going to do is going to stretch and squeeze this ring of particle in certain fashion. And these certain fashion basically explains the two polarization states of gravitational wave called the plus and cross polarization, as you see on the screen. So this basically is telling us that these propagating fluctuation which these gravitational waves are in the space-time curvature, they produce an oscillating tidal force, a tidal field. And this was predicted by Einstein's general relativity theory in 1916. And today we have really seen it. If I'm talking about gravitational wave, I cannot miss talking about the first detection of gravitational wave, which was made on 14 September 2015. This detection was done by LIGO Observatory, that is Laser Interferometer Gravitational Wave Observatory. So what was seen in the first detection is basically the merger of two black holes of stellar mass. By stellar mass, we mean something between, let's say, tens to few tenths of mass of the sun. So the two black holes which were observed to be merging and then collapse together were initially having mass of 36 times mass of the sun, and the black hole uh, having mass of 29 times mass of the sun, and they merged to form a new black hole of mass 62 times mass of the sun. And you can see the difference. The new black hole which formed had mass 3 solar mass less than the total of initial black holes, which means that this energy equivalent to 3 times mass of the sun was emitted in the form of gravitational wave. And this signal, this gravitational wave, is something that the LIGO saw at two different sites, one at Hanford and one at Livingston. And this is the signal that they saw. Y-axis here is the strain. I'll explain what the strain really is. And the first plot that you see is something that the observatory really saw. And the second plot that you see is something that they predicted from the theory, or from the numerical relativity. And the difference of these two is shown in the third panel. So telling us that yes, what is being predicted and what is being seen is really matching. And at the bottom that you see is the frequency of the gravitational wave. And so this is basically a map, a heat map, where it's telling that as the signal evolves, the signal really lasted only for 0.45 seconds. And as it goes from 0 to 0.5 second, the frequency of gravitational wave was increasing along with its amplitude. So both amplitude and the frequency of this signal was increasing. And the end of the signal that you see is the point where a new black hole of 62 times mass of the sun has formed. So this is about the first detection. And if you're wondering how this was really done, I'll just briefly explain to you how LIGO really works. So it's a ground-based detector, which means that it is on Earth. It is having the shape of, it's having two long arms, and the length of these two arms is around 4 kilometers. And what you have at the end of these arms are two mirrors. And at the cross section, what you have is called beam splitter. So what you do is basically you shoot laser at these two arms, and this laser reflects back from the mirror and comes back at the beam splitter. If there is no gravitational waves and if there is no noise, what you expect is that when the laser comes back and these two laser beam, when they meet, the light waves should cancel out each other. That's how the experiment is really designed. But if there is gravitational wave passing through this detector, then what you're going to see is that when these two laser beams are combining, they're going to form an interference pattern. This interference pattern is going to give you the information about the gravitational wave signal that has passed through. So that's how roughly you can understand is this LIGO detector had detected the gravitational waves for the first time. But can we see all kinds of frequency of gravitational waves using LIGO? So as I showed in the previous plot, the frequency of this gravitational wave event was varying from 30 to around 500 hertz. That's a particular range. But can we go down? Can we have a frequency of gravitational wave very small or very large? Well, there can be, but that's not where LIGO detector is sensitive. So as I talked about the frequency of gravitational wave, I just wanted to motivate that it's nothing but very similar to electromagnetic spectrum. So we know today that electromagnetic spectrum has different electromagnetic waves, all the way going from gamma ray, X-ray, UV, visible light, infrared, microwave, and radio. And what really is varying going from gamma ray to radio is the wavelength or frequency of these electromagnetic waves. Very similar to this, a gravitational wave also have a spectrum, and which now today we call it as astrophysical gravitational wave spectrum. So what you really have in this spectrum is, on the x-axis you have the frequency of gravitational wave. So LIGO lies in this particular region. I hope you can see my cursor. So this is the region of few hundreds of hertz frequency, where LIGO is sensitive. And this is a ground-based detector that I also talked about. Uh, there is another frequency range which is around millihertz, where the space-based detector will be sensitive detector like LISA. And if we go towards very low frequency, that is around nanohertz, that's where the pulsar timing array comes in. So just to explain, the y-axis here is the strain. Strain is nothing but a quantity where it's basically delta L by L. What is L here? So L is the length of the arm of the detector. And what you want to measure is the change in the length of this arm when gravitational wave passes by. As I told you that it's going to squeeze and stretch the ring of particle. In the similar way, it's going to squeeze and stretch the arm of the detector. So what you want to see is the change in the length. That's delta L, and divided by L is the strain. So that's what you have on the y-axis. So you might be wondering, okay, I know that black holes of 30 solar masses, when they merge, they give rise to they emit gravitational wave at hundreds of hertz of frequency. But what would really give rise to gravitational wave which is having frequency of nanohertz? Well, you can try to understand it with a simple formula. So the gravitational wave frequency, let's call it F naught, is if you calculate it through general relativity, it's inversely proportional to mass. So in this formula, if I put mass to be very, very high, let's say around 10 to the power 10 times mass of the sun, the frequency that I'm going to get is of the order of 10 to the power minus 6, so which is around thousands of nanohertz. So which means that the nanohertz gravitational waves must be emitted when very, very high supermassive black holes are merging into each other. So the process is the same. Black holes are merging, but the mass of this black hole which are merging is different. So if we have smaller black holes, you're going to detect gravitational wave through LIGO. If you have supermassive black holes which are merging, you're going to see gravitational wave in the nanohertz frequency range. Okay, so talking about supermassive black holes, well, when the two supermassive black holes are coming closer to each other, they are going to form a binary system, and that's what we call supermassive black hole binaries. And how are they really going to form? Today, we are very, very sure that each galaxy in the universe harbors a supermassive black hole at its center, which should have mass around 10 to the power 6 to 10 to the power 10 times mass of the sun. And you must have seen this beautiful picture by Event Horizon Telescope, which showed the first image of a black hole at the center of M87 galaxy. So this is another evidence that yes, each galaxy harbors a supermassive black hole at its center. So we also know today that in the universe there are millions to billions of galaxies, and we expect that each of these galaxies in its lifetime must have experienced or must have merged with the another galaxy. So when these two galaxies are merging, the supermassive black hole sitting at the center of these two galaxies are going to come closer and closer. So, and they are going to make this binary system, which means this merger event of these galaxies are going to make the supermassive black hole binary system, and that's what is going to emit nanohertz gravitational waves. Now, talking about the nanohertz, it's very, very small number, and if you convert it into the time scale is of the order of decade. So, which means the signal itself is lasting for a decade. I mean, the variation in the signal is of the order of decade. And if you calculate the, I'm sorry, there is a background noise. Is someone asking a question? If there is no question, please mute.
I think it was an accident.
Okay. Okay. So,
Excuse me,
yes.
ma'am, you said that gravitational wave can increase or decrease the length, right?
Yes.
So, like, for instance, you the experiment of the LIGO, how much centimeter or meter does the height changes? Like,
Hmm.
not height or
It's a very
meter.
good question. Actually, the variation is extremely, extremely small. So I told you that the length of the detector is around 4 kilometer, right? For this length, the variation that you expect to see is around 10 raised to power minus 16 centimeters, which is um, 1 by 200 times radius, uh, um, radius of the proton. So that kind of small change that LIGO detector actually saw, and you can imagine how sensitive it must be, what kind of engineering must have gone into it. That's something we have never, scientists have never achieved before.
So now, if you're saying we are changing the size of proton, is it true then I say it? But this we are changing the size of one proton.
Could you please repeat? There was some noise.
So by doing this, we are changing the size of a proton or subatomic particle, right?
Okay.
Is it what it mean when we say gravitation waves?
Well, you can say you can imagine something like this. So those rings of particle that I was showing you, if they were sitting at the two ends, or like at the diagonally opposite ends of a proton, then the variation between them will be like this. But you cannot say that there is a variation within proton itself. But you can say that the amount of stretch that you expect for a length of 4 kilometer uh, is that much. But that is something that will give rise to a strain of 10 raised to power minus 21, which LIGO saw. But let's say you have even longer arm, okay, very, very long, which means that the strain, which is actually 10 raised to power minus 21, okay. So you see the strain value is around 10 raised to power minus 21, okay. And if my length of the detector increases, you can multiply it by the strain, which means the delta L will also increase. So this quantity which I'm telling you is with respect to the length of the detector. So if you have larger M, the delta L will also be large. That's what I meant.
Okay, like it does not create any change in subatomic particles.
I know, I don't know. Yeah. It's all about the length of the detector.
Thank you.
Yeah. Okay. So where was I? Huh. So the wavelength, if you try to calculate the wavelengths of these gravitational waves, it will be around 10 to the power 16 meter, and that's very, very high. Okay, and that's actually few parsecs. So which means if I have a signal which is having a wavelength so large, and if I want to detect a signal like that, I need to have a detector which is actually uh, larger than this wavelength. Obviously, I cannot, or anyone on Earth cannot make such a detector which is so large. It's actually larger than the size of solar system itself. Um, so what do we do? I will talk about that. But before that, as I said, there are so many galaxies in the universe, and because there are so many galaxies, and assuming that each one of them are going to experience at least one merger event in their lifetime, assuming that we expect a total of of the order of 10 to the power 10 galaxy mergers in the universe. It means that there is not just one event happening. There are many, many events happening in the universe. So what would happen then? Well, what we are going to have is a background. You can imagine it that the gravitational waves emitted by each of these merger events in the universe superimpose over each other because there is large population of supermassive black hole binaries, and then they form a stochastic background signal. You can imagine it very similar to the pattern that you see on the water surface when rain has started. Just when the rain stops, what you see is that no droplets falling, but what you see is a very nice pattern. So you can imagine it's something similar to this. So which means that each of these signals are superimposing and making a background pattern in the space-time fabric itself. And how would this really appear in terms of the strain I was talking about? So astrophysicists had already predicted earlier that uh, the the characteristic strain should follow a unique power law shape if the gravitational wave background exists in the universe, and that should look something like this dotted line that you see on this plot. So x-axis here is the characteristic strain, y-axis is characteristic strain, and x-axis is the gravitational wave frequency. And this is the formula that the astrophysicists predicted that characteristic strain of a gravitational wave background should follow, where alpha was theoretically found to be 2 by 3, and a here is the amplitude. So you might be wondering what are these different patterns on this plot. Actually, when a merger is happening, supermassive black holes coming closer and closer, and these galaxies are coming closer and closer, what is really assumed is that the orbit between the two black holes is shrinking, mainly because the energy is being carried out of this system in the form of gravitational waves. If that simple scenario is there, then you would expect this dotted line. But let's say that is not the case. What if the supermassive black holes are interacting with the stellar population that they have within the galaxy itself? And that's what we really expect, because there are so many stars and many things in the galaxy, and when these galaxies interact, the supermassive black hole is going to interact with its surrounding, and that also affects the shape of this power spectrum. So this is what these different regions are really showing. So if there is a disk around a supermassive black hole which is viscous, then you would expect that, okay, this unique power law might change within this red region. If the supermassive black holes, when they are coming closer, if they are not in circular orbits, but if they are in eccentric orbit, that also will affect the characteristic strain, and that's what is shown here in the green region. And also, what is the population of supermassive black hole binaries in the universe? That also affects the characteristic strain, and that is shown here in the blue region. So all these factors really, really matter. And but in the simplest scenario, what we expect is alpha should be 2 by 3, and we should have a simple power law. So that's what is something theory is saying, theory is telling us. Now, talking about gravitational wave background, I should definitely talk about how do we really detect. I was talking about the ground-based detectors, but how do we really detect these very low frequency gravitational wave background? Here comes the pulsar timing array. Now, what is pulsar timing array? Well, as I said, we cannot really build a detector. Human cannot do that, but thankfully, nature has given us natural detectors. So we call them millisecond pulsars. So these millisecond pulsars are nothing but neutron stars, and they are rotating very, very fast. So fast that the period of the rotation is of the order of milliseconds. And what we really observe from these millisecond pulsars are radio pulses, and I will talk about them in more detail. So when we have many millisecond pulsars in the sky in our own galaxy, you can imagine that let's say you have 3 pulsars as also shown in this picture, then Earth to pulsar number 1, Earth to pulsar number 2, and Earth to pulsar number 3. All these line of sights are itself going to act like the length of the detector. So you have many arms of the detector in the sky. So together, this array of millisecond pulsars form a galaxy-sized gravitational wave detector. And I will tell you how that really happens, but you should also look at this beautiful picture by one of our colleague, Neil Kohli from InPTA. He's trying to show here that when there are many galaxy mergers happening, each one of them emitting gravitational wave, it's making a background signal, and that background signal is also perturbing the space-time around each of these pulsars, and this perturbation near the pulsar is going to affect the light arrival time of these pulses seen from pulsars as they seen at Earth. So gravitational wave basically is going to alter the time of arrival of these radio pulses coming to us, but emitted by the millisecond pulsar. So you should keep in mind that the millisecond pulsars are used as the tool to detect gravitational wave background. Millisecond pulsars are not emitting the gravitational wave. This is a very common confusion many people had, so I just wanted to clarify that. So how gravitational wave, when it is passing through an array of pulsar, is really going to affect the time of arrival of the pulse on Earth. So what it's going to really do, it's going to, as I said, it's going to induce a fluctuation in the space-time around the pulsar. And what that fluctuation is going to do is going to change the pulse frequency. So when I told about the rotational period, inverse of that rotational period is pulse frequency. This perturbation due to gravitational wave background is going to affect the pulse frequency of the pulsar itself. And this formula basically describes how this delta nu by nu, basically the fractional change of pulse frequency of the pulsar, it's going to be the function of this alpha, beta, gamma, where these are the pulsar's direction cosines to x, y, z. So basically it's telling you the direction of pulsars in the sky. And then you have this delta H plus and delta H cross terms. These are basically the delta H is again, it's strain, but it's a perturbation in the space-time itself with plus and cross polarization, which I was talking about. And this was very nicely derived by Dittweiler in 1979. So in short, a time-varying influence of gravitational wave is something that you're going to see in the local space-time of Earth and pulsar. Or you can also imagine it like there is Earth and pulsar system, this whole arm, this whole pulsar and Earth arm detector is itself going to stretch and squeeze, and that's going to perturb the time of arrival of the pulse on Earth. So theoretically, what this is going to do is going to induce something called residuals. I'll explain what residuals are, but mathematically they are basically the integration of fractional change in this pulse frequency. So the aim of pulsar timing array is to search for this residual, which is induced by gravitational wave background. So this is something that comes from theory, but in reality is a bit different. So before I talk about residuals, I should definitely talk about why millisecond pulsars are so important. So millisecond pulsars, as I said, these are very fast rotating neutron stars, and they rotate a few hundred times within a second. And this rotational period is of these millisecond pulsar is very stable. So as you can imagine that you see hundreds of pulses coming to Earth, within a second. And why do you really see these pulses? It's basically because when the neutron star is rotating from these magnetic poles, there is emission of accelerating electrons and accelerating particles. And when this cone passes through the line of sight of Earth, it's going to give rise to a pulse. That's how we see these pulses. So each of these pulse coming, very, very fast, that's what we observe using radio telescopes. And these are these are called perfect galactic clocks, because as I said, these rotation periods of millisecond pulsar is very, very stable. So what we really do, we observe these pulses, and what we just add them, we stack them over their rotational period. We stack many, many of them, at a few thousand of them together, and that gives us an integrated pulse profile shape. And that pulse profile shape, as it is shown here, is something extremely stable, and it's known to be very, very stable for a given millisecond pulsar. And using this pulse profile, what we really measure is called time of arrival of pulse. And this can be precisely modeled, and it can also be precisely measured. So what we are really doing in pulsar timing array, we are keeping track of this rotation of pulsars, this rotation period of pulsar, for a very, very, very long time span. So what we really have is the measured time of arrival of the pulse, and also predicted time of arrival of pulse. This predicted time of arrival, or in short TOA, is something that comes from the model of the pulsar itself. And this model of the pulsar can be obtained very accurately using the art of pulsar timing. So what you really do is you observe the pulsar for a long duration of time. You measure these TOAs, or the time of arrivals, and what you do, I should explain this first. So what you really do, you measure the time of arrival as shown here. So you have this pulse number 1, 2, 3, that's your data. And in blue, what you have here is the predicted time of arrival for a given model of pulsar. What you find is the difference between them. The difference between them is something we call timing residual in pulsar timing method. And this timing residual is expected to have certain shape, certain systematics. As in this particular example, this residual is expected to increase with time, because the difference between the pulses is increasing, as you see, as the pulse number is increasing. So what we really do in pulsar timing, we try to remove any of these systematic, and we try to make these residuals completely flat, or we call them white noise, which basically tells that it's just a noise, it's not dependent on time. So when we make these residuals completely flat, we do that by fitting more and more parameters in the pulsar model. So there can be various parameters, like if the pulsar is in a binary system, there can be binary parameter, there can be position, RA and deck of the pulsar, there can be parameter related to interstellar medium between Earth and pulsar. So you can fit all those parameters by using this method of pulsar timing. So using the pulsar timing, you are making your residuals flat. At the same time, you are getting a very precise pulsar timing model. So this is what the pulsar timing is. So in short, using the figure, I would like to show that, okay, you have this cone of beam that's passed through your telescopes, you receive it, and what you get, this very stable mean pulse profile, and you measure the time of arrival. And using this procedure, we measured this time of arrival with a precision of sub-microsecond. You can imagine the kind of precision it is. And hence, so if today I measure the time of arrival of a given millisecond pulsar, I can predict what would be the time of arrival of the same pulsar after 20 millionth rotation of that pulsar. That's the kind of precision we have. So I can easily predict what will be the time of arrival after so many rotations in the future. So now you understand that using pulsar timing, I can find something called timing residuals. And in these timing residuals is something we expect that the signal or gravitational wave background would be present. So from here, what we are going to do, we are going to work with these timing residuals. So that's what the pulsar timing array really does. So this point is not really very easy. So I would like to take a pause and ask if anyone has any question.
So I just have a small doubt. So the stacking part that you mentioned over there, so like we generally use the mean stacking method itself, right?
What do you mean by mean stacking method?
Like mean stacking in the sense like just like directly stacking over like one over the other, and then the most prominent peak will be the time period that we are looking for.
Yes, so you stack in a way that you stack over one period. So let's say the period is 2 milliseconds. So you're going to stack after every 2 milliseconds. That's how you do it.
Oh, okay.
Any other question? Okay, so everyone understood everything. So from here, what we are going to work with is these timing residuals. Now, how would the gravitational wave background look like in these timing residuals that we are basically deriving from our data? So what gravitational wave background is going to do, that timing residual that we have, remember the timing residual that we have are for many pulsars, okay, not just for a single pulsar. So it's going to create a common red noise in the signal. So when I say common means common in the timing residuals of all pulsars. And when I say red noise, it means that if I take a Fourier power spectrum of the timing residuals, the power spectrum should look like a power law where there is high power at low frequency and there is low power at high frequency. And that power law, that kind of power law of the red noise is given by this equation. And this is related to the previous alpha that I was talking about. If you derive this new power index of the Fourier power spectrum will be dependent on alpha by 3 minus 2 alpha. So if alpha was 2 by 3, this gamma is expected to be 13 by 3 simply. So this is what pulsar timing array is trying to find out. Do we really see a power spectrum which has a spectral index of 13 by 3, which has a certain amplitude, which is A? But is that enough? Well, answer is no, that is not enough. We also have another factor sitting here, which I have shown in red. What is that? That is something called a correlation. This correlation is very specific to the supermassive black hole binary gravitational wave background, and this is specific to it and governed by the quadrupole nature of the gravitational wave. So if you're wondering what is this quadrupole nature, this is basically, you can just imagine in electromagnetic waves, we know that we have dipole radiations, right? We do not have monopole because charge is conserved. In gravity, mass is conserved, hence we do not have monopole radiation. But angular momentum is also conserved, hence we don't have dipole radiation. So what comes next? Next comes the quadrupole nature. So the gravitational wave is quadrupole radiation. And astrophysicists derived that because of this nature of gravitational wave, the residuals from different pulsars should be correlated to each other. And this correlation, which is called HD correlation, or in full form it is called Hellings and Down correlation, was found to be the function of the angle between any two pulsars that I see in the sky. So if I have pulsar 1 here, pulsar 2 here, the angle between them is what is shown on the x-axis. And the correlation between the timing residuals of different pulsars is expected to look like this as a function of the angle between two pulsars. So, which means that gravitational wave background is not just going to make a common red noise in the power spectrum. It's also going to it's also going to create a correlation called Hellingsen-Down correlation in the timing residuals of the pulsars. So it's important that when we want to say that we have really detected gravitational wave background, we, along with common red noise, we also see this SG correlation together. When we see both of them together, then we will say that we have really seen gravitational wave background. And this is a very nice small GIF by NANOGrav collaboration, which shows you that so at the center you have Earth, and then in sky you have various pulsars. The angle between any two pulsars is going to is basically shown at the x-axis. So if there is no gravitational wave, you do not see anything. You should just expect it to be flat. But if there is gravitational wave, what you expect is that angle as a function of this angle, you should have this kind of correlation called Hellingsen-Down correlation. So you have understood that in the timing residuals of these pulsars, we want to see both of these signatures, common red noise and the correlation. Okay, so that's what PTAs are really after. They are behind these signals, these signatures. And you should also know that there is not just one pulsar timing array in the world. There are many pulsar timing arrays. One is the NANOGrav collaboration, which is North American nano-hertz observatory of gravitational waves. It uses different radio telescope, Arecibo Very Large Array, Green Bank Telescope, and Chime. Along with that, there is European Pulsar Timing Array, which uses Effelsberg Telescope, Lowell, Nancy, WSRT, etc., etc. We have our own Indian Pulsar Timing Array, which make use of the Giant Metrewave Radio Telescope in Pune, very near to Pune. And Indian Pulsar Timing Array, I should mention that it's not just Indian collaboration, it's Indian-Japanese collaboration. So other Pulsar Timing Array is PPTA, which is Parkes Pulsar Timing Array in Australia, which uses Parkes telescope to do PTA studies. And there are newly emerging PTAs also. One is called MPTA, which is Meerkat, which is making use of Meerkat telescope in South Africa. And then we also have Chinese PTA, which is using FAST telescope, which is one of the best radio telescopes in the world. They also have their own Pulsar Timing Array. And together, many of these collaborations together make the International Pulsar Timing Array. So, as I told you, I work very closely I majorly work with Indian Pulsar Timing Array. I thought I'll describe a little bit about that. You may go through our websites for more details, and also follow us on different social media handles. So Indian Pulsar Timing Array uses the unique strength of upgraded Giant Metrewave Telescope. This is an interferometer which has 30 parabolic dishes with 45-meter diameter each. This instrument is very, very sensitive at low radio frequencies. When I say low radio frequencies, which means around 300 megahertz to 500 megahertz, these are very low radio frequencies. And such radio frequencies are very ideal to study the effects due to interstellar medium. And those effects are dependent on radio frequency, and they're very, very dominant at low frequencies. So uGMRT is ideal to study such effects. And in fact, PTA is highly affected by the effects of interstellar medium on the pulse arrival time, which I will explain in more detail. So InPTA team this is few of us. We InPTA team try to meet every 6 months for something called Busy Week, where we sit together and work on various projects. and try to push our projects together. So as I said, it's Indo-Japanese collaboration. There are 10 faculty members, 8 postdocs, including myself, and 12 PhD students and 9 undergraduates. The experiment started in 2015, and presently we are observing around 22 millisecond pulsars using GMRT with a cadence of 10 to 14 days, which means that after every 10 to 14 days, we observe each of the pulsar. And currently, we are planning to extend our sample to more pulsars in future. So Indian Pulsar Timing Array made its first data release last year, which we call as InPTA DR1. This data release had data of 14 millisecond pulsars. The name of these pulsars are listed here. If you're wondering what these numbers really are, these are basically array and deck of these pulsars. So this is just a sky distribution of these pulsars. So red dots here are all these InPTA pulsars, and the gray dots here are those pulsars which are in the sample of International Pulsar Timing Array. So as I said, uGMRT is very sensitive at low frequency, and we make use of that frequency. We observe our pulsars simultaneously in 2 frequency bands. One is band 3, another is band 5. Band 3 is from 300 to 500 megahertz, and band 5 is above 1000 megahertz to 1460 megahertz. So you can see the bandwidth of each band is around 200 megahertz. So the data that was released last year was spanning around 3.5 years. So the data was that long. And what this data really contained is something called dispersion measure. I will explain what that is. And as I have already explained, it also contained time of arrival of the pulses. And as the most important thing for pulsar timing array, our data contained timing residuals, which are the difference between observed and expected time of arrival. So dispersion measure, what really this means? So as I said, when a pulse passes through the interstellar medium, it's coming from pulsar to Earth. What this interstellar medium really has is ionized gas with free electrons. These free electrons are going to scatter these electromagnetic waves, which are the radio waves coming from pulsar to Earth, and it's going to cause a delay in the arrival time of these pulses. And this delay is a function of radio frequency itself. So if I'm observing my pulsar from, let's say, 300 to 500 megahertz, then it means that this F1, F2 are basically the 300 and 500 megahertz frequencies. So, and this time of arrival is proportional to this constant quantity called dm. When I say constant, this is constant with respect to the radio frequency. But as you will also see later, that dm is something that varies with time. So this is telling us that because this is inversely proportional, this time delay is inversely proportional to f to the power minus 2, telling us that the low frequency wave is going to travel slower and it's going to arrive later on Earth than the high radio frequency wave, which is also actually shown here. So what you really see here is these timing residuals, and these are these timing residuals as a function of radio frequency. So as you see, the time of timing residuals at lowest frequency is having highest residuals, and at the highest frequency it's having the lowest residual. It's telling us that the lowest frequency is arriving much later and the highest frequency is arriving faster. And if I really want to do gravitational wave search, I need to make sure that I correct for this effect. So what we do is, to correct for this effect is we fit for this dm quantity. Once I fit it, what I am going to see is something like almost flat signal. So here these residual are in band 3 and here it is in band 5, and you can clearly see the effect of this time delay is much less in band 5 because band 5 is at high radio frequency. So this kind of correction that we need to make in the timing residual, this process is called de-dispersion. So once your pulse is de-dispersed, you have corrected for this effect, this is how your pulse will look like. So what you really see here is the intensity of this pulse as a function of radio frequency. Y-axis here is the radio frequency, and this bright signal is basically showing you the intensity of the pulse. And x-axis here is the pulse phase. So as you know that pulsar is rotating, so one rotation corresponds to one phase. 0 to 1 phase is one rotation. So if I have done the de-dispersion, if I have corrected for this time delay effect due to dispersion happening in the interstellar medium, then this is how my pulse would look like as a function of radio frequency. So this is what we did in our data release. We estimated this dispersion measure for each of the pulsar as a function of time. Because we have 3.5-year long data span, the dispersion measure has to be estimated for each of the date of observation that we have. So this is what we have shown here. So what you see here is basically the DM, and as a function of time, these are basically date, modified Julian date. And you see for all these 14 pulsars, the DM is actually varying, it's not constant. And sometimes you actually see the variation to be quite slightly periodic. And I should mention that the kind of precision that we obtained using GMRT in InPTA is of the order of 10 to the power -4 to 10 to the power -6 parsec per centimeter cube. That's the unit of dispersion measure. So this is unprecedented precision. It has not been obtained by any other PTA across the world. So that's the strength of Indian Pulsar Timing Array, because we have low radio frequency observation with us using uGMRT, and we should be really proud that we have such sensitive instrument in India. So this is one example of the timing residuals that had been blabbering about. So again, the third and fourth of these panels are showing you the residuals as a function of the date, and the above two panels are basically showing you the DMs. So this is what we have as a part of our data release. But what do we really do? Can I just directly take these residuals and search for gravitational wave background? Well, it's not that straightforward. We take these timing residuals, and first what we need to do, we need to extract out certain noises that are really present in the data. What are these noises? These noises are of different categories. One is something called white noise. White noise is called white because it is not dependent on the frequency of the variation of the noise itself. This is majorly caused by the instrument itself. So these are noises at the instrument level. And the other noise is called spin noise. So when I was saying that the rotation of the pulsars is something very, very stable, well, it is stable, but it does vary at the time scale of years. Okay, so the spin of the pulsar is varying at the time scale of years, and that would appear in the timing residuals, and it's going to vary my timing residuals at the same time scale at which the gravitational wave also exists in the timing residual. So I need to make sure, so it's sort of covariant with the gravitational wave signal. So I need to make sure that I remove the spin noise. And I have written achromatic word here. Achromatic means that it is not dependent on radio frequency. So this noise is not dependent on radio frequency. And the third category of noise that exists is chromatic noise, which as also mentioned here, is dependent on radio frequency. And this chromatic noise is majorly caused by the ISM itself. And that is the strength of InPTA, as I also mentioned, that we can measure the dispersion, measure the dispersion measure very, very precisely. And using that dispersion measure, by looking at how dispersion measure is varying, you can model how the chromatic noise will be there in your timing residual data. So that is the strength of InPTA. So once we have the hold on all these noises. We subtract out these noises from the timing residuals, and what we get is these filtered timing residuals. Okay, and we use these filter timing residuals to do any kind of search. It can be gravitational wave background search, it can be a different kind of gravitational wave search, etc., etc. So just wanted to mention that there are some important noise sources that exist in the timing residuals. So what is the next step for Indian Pulsar Timing Array? We are going to have another data release very soon. It's expected early next year, where we are not just going to have data release for 14 pulsars, we are going to add some more pulsar into it, and we are going to have a sample of around 29 pulsars. And in this data release, the time span of the data will be around 5 years. And this data release will also have band 4 observation, which is a band between band 3 and band 5. And we are going to obtain the model of the pulsar using this large 5-year long time residual baseline. And we also plan to model the chromatic noise or the achromatic noise that I just told you about in each pulsar. So that's the aim that we have for our second data release. I should also mention that these noises that exist in the timing residuals, these chromatic and achromatic, are also red noises, very similar to the gravitational wave background. And I already mentioned to you that red noise is something which has a high power at low frequency and low power at high frequency. So these are also red noises. So it's very important to remove them to really find out the actual gravitational wave background signal in the data. So I've spoken about timing residuals, I've spoken about pulsars, I've spoken about Indian Pulsar Timing Array. Let's come to what we are here for. So most of you know that there was announcement on June 29 this year, and this was a coordinated announcement by various PTAs across the world, including EPTA, InPTA, NANOGrav, and PPTA, and there was many news articles. So on this date, if you had gone on archive in the morning, you would have seen around 15 papers by these collaborations. So what was really going on? So in this work, EPTA and InPTA had combined their data together to search for gravitational wave background signal. Independently, NANOGrav and the Parkes Pulsar Timing Array had also done their independent gravitational wave background search, and they announced their result on June 29. So first I'll talk about EPTA plus InPTA. So EPTA has around 25 pulsars in their sample, and this is their second data release, hence it is called DR2. So the full data set, which they call as DR2 full, has time span of around 24.7 years. And they are also using a subset of their data set that is called DR2 new. That has a time span of 10.3 years. If you are wondering why they really use a subset of their data, it is because this DR2 new data, which is around 10.3 years long, this was obtained by using upgraded instruments at their telescopes, various telescopes. So they wanted to make sure that when they made the upgradation at various telescopes, they would like to analyze that data set separately, and they also thought that we should analyze the full data set together. So they have done independent two analysis. So that is one thing. Other thing is EPTA and InPTA have 10 pulsars in common. So for these 10 pulsars, they combine their data with the InPTA, and when they combine their data with InPTA, that increased their baseline for the full data set to 25.4 years. And for the DR2 new data set, the timeline was around 11 years. So what was really seen? This is what was seen in the data set. What you see here is the correlation that I was talking about, the HD correlation, as a function of angular separation between pulsars. So if you're wondering what are these voilents here, so each of these voilents are basically posterior distribution, or you can call them probability distribution of this correlation. And each of these violent correspond to a particular bin for the angular separation. So you have around 10 bins here, so you see 10 violents, and you can see different colors here. You see red, you see orange, you see green and blue. These are basically the 4 different data set which I just explained to you: DR2 full, DR2 full plus, DR2 new, and DR2 new plus. So what was really seen is that the red one and the orange one, which is DR2 new, it was found to be very close to the Hellingsen-Down correlation. But this DR2 new data was found to have the gamma spectral index, which I told you that is expected to be around 13/3, also indicated here by this dotted curve. So it was not found to be very close to 13/3. So basically, DR2 new set is following the SG correlation, but it is not having 13/3 spectral index, or it is not very close to 13/3 spectral index. So there is some tension there. However, the full data set, both DR2 full and DR2 full plus, it was found to be less close to the SG correlation, but it was found more close to 13/3 spectral index. And on y-axis here is basically you see the amplitude of gravitational wave. So if you are wondering what are these contours, these are basically 1 sigma, 2 sigma, and 3 sigma contours of the amplitude and spectral index. So yes, we are close to seeing energy correlation. We are also close to seeing a certain spectral index, which is close to 13/3 within the 3 sigma level. And here is basically the values of the amplitude and the gamma that has been found using DR2 full plus and DR2 new plus data set. So if you're just wondering again, what is this plus? Plus means that InPTA data has been added there. So this is what EPTA and InPTA found. Pretty cool. We have really seen the evidence of gravitational wave background with 3 sigma significance. If you are wondering what is the use of adding InPTA, I have mentioned it multiple times earlier. The InPTA data set is very good at modeling the chromatic noise, which is due to ISM. So this is one example of one of the pulsar 1744 minus 1134. What you see here are basically the probability posterior distribution of the chromatic noise amplitude and DM noise amplitude and DM slope. If you're wondering what these really are, these are basically the parameters of the red noise due to DM and red noise due to achromatic signal. So if you can see, once the DR2 full data was analyzed, they couldn't constrain these values properly. You see this double hump here. But once the InPTA data is added, the noise is very well constrained. You see very nice Gaussian kind of signal. So this is the effect of InPTA data. We are able to constrain the ISM noise very nicely. This is the main advantage of adding InPTA data into EPTA. And this is what independently NANOGrav saw. NANOGrav has around 67 pulsars in their data set with 50 years of baseline. They also saw SG correlation with around 3.5 sigma significance. As you can see, they are much better. And this is mainly because they have more number of pulsars. So you can basically sample this correlation better than others. Similarly, Parkes Pulsar Timing Array also saw such correlation. They used a data set of 30 pulsars with 18 years baseline. Their results were also found to be consistent with other PTAs. So this is the main result. Yes, we have seen gravitational wave evidence of gravitational wave background. right now, PTA community and scientists are really not calling it a detection. We are calling it emerging evidence, because the significance of seeing this SG correlation is around 3 sigma, and what we really expect is around 5 sigma. So the road ahead is the International Pulsar Timing Array. What that is going to do, all the PTAs, InPTA, EPTA, NANOGrav, PPTA, and MPTA going to pool their data together and create a new data set, and that will have around 115 pulsars. You can imagine what kind of large data set they're going to be, and it's going to cover more than 20 years of time baseline. And we are going to analyze that data. We are going to model the noises, different noises that I talked about, and then there will be search for gravitational wave background. And if you're wondering what will be the use of having larger and larger data set, see, larger data set basically means that inverse of that data set. So if t is the time span of your data set, 1 by t is the frequency, which will be very small, which means that you will be able to see the lower end of the spectrum where you actually expect high power, because it is red noise. So looking at such low frequency part of the spectrum will give you more insights into how supermassive black holes really evolve. What is the evolution of these black hole binary system in the universe? And there will also be efforts to discover gravitational wave signal from the individual black hole binary system, very similar to LIGO. What LIGO saw was one particular event. It's called transient event, and they saw the signal from one particular event. It was not a background. Similar to that, we also expect that we should see the signal from individual supermassive black hole binary, but that requires much more precision. So this is what right now I'm also working on. I'm working on combining the data set under the consortium of International Pulsar Timing Array, and we are going to have this data set ready for by next year. So keep an eye for another year. It's going to be more exciting. So here is where I'm going to leave. So yes, we have opened a new window to ultra low frequency gravitational waves, and what is seen independently by various PTAs is a common red noise signal, which is also correlated spatially. Spatially means as a function of angle between the pulsars, and it's a strong emerging evidence of gravitational wave background. And InPTA collaboration had combined its data set with the European Pulsar Timing Array, and right now we are working on combining data set of all the PTAs, which will be the third data release of International Pulsar Timing Array, and we are waiting for 5 sigma detection. So that's what I believe. Thank you.
Excuse me, ma'am. I have a little doubt.
Yes.
Yeah, actually, you've mentioned using sigmas to reduce noise, right? 1 sigma, 3 sigma. So, provided we use TGSS to observe these PTAs, these pulsar, what do you call the pulses. If we use 5 sigma and 7 sigma, won't it be even, what do you call this, peculiar?
See, when I'm saying 1 sigma, 2 sigma, 3 sigma, this is the significance level found in the data set when I'm searching for any signal. So if I have a data, if I have a model, okay, and I want to see that whether this data is following this model or not. To do that, what usually astronomers do, they do Bayesian analysis, and they found what is the significance, what is the confidence at which I can say that yes, I have seen this model in this data set. That's what is called significance. Significance is not something I have priorly in my hand and then I do my observation. It is something that I try to find in the data set.
Okay, ma'am. And the other question is, the TGSS is radio interferometry, right?
TGSS.
Yeah, Tata GMRT.
Okay.
So why can't we use any other wavelengths to do this PTA?
You mean radio wavelength?
I mean, yeah, the GMRT use radio wavelengths, right?
Yes.
Yeah, why can't we use IR, UV, or optical?
Okay, so it's a good question. So see, these pulsars what they are emitting are the radio pulses. Okay, so although pulsars are also visible in other wavelengths, but the radio pulses that we see are something very, very accurately modeled. Okay, so this is because of this reason that we do observation only in radio.
Okay, ma'am.
And they are bright in radio.
And ma'am, the other question is, you said that these mergers are found using the help of pulsars, right? So I have a question. Say suppose you have mergers far away and a merger nearby, and consider I mean, provided the damping of gravitational wave, when the both the pulses reach us at the same time, and both of them suppose have a same value, na? How can you differentiate both the mergers?
So right now, by looking at the data, we cannot differentiate. So it's very much similar to that. I gave that example of water surface, right? So what you're saying is that if I have one drop here, and I'm observing at this point. Okay?
Yeah, but the first drop has larger intensity, so that when both the ripple reaches you, it reaches with the same amplitude. So how can you differentiate both of them?
You cannot. So and you do not just have two drops. You have many drops. So that's why it's called a background. So as I mentioned, we are expecting around 10 raised to power 10. I mean, we are being very generous here, but at least there are going to be thousands of mergers. So there are thousands of drops. Okay. And so hence we have a background, not just one or two signals.
Okay, ma'am. The reason why I asked you the 5 sigma values is actually I do a multi-wavelength astronomy research in in Radatom Collaboratory. They are powered by this GMRT, and we eliminate the background radio noise using 3 sigma and 5 sigma values. And 5 sigma is very rare case scenario. Hence, I asked the question.
Okay.
Thank you.
Sure. Thanks.
Hello, Dr. Prerna.
Hello.
Yeah, Sanket, go on.
Yeah. So can we do the parameter estimation with this data? Is it possible, or do we have to do some new technique to?
Well, what we are really doing is parameter estimation itself, but that is using the Bayesian analysis. And what are these parameters that you are estimating? These are the parameters.
I mean the masses and masses of a black hole and all those things.
Okay, that's a good question. Well, see, this is a gravitational wave background. So right now, since there are so many sources which together have made the background, it's difficult to talk about individual sources. But in future, as I also told about IPTA, IPTA is going to have effort to discover individual sources. So once you have individual sources, there you know that okay, I have seen this signal. This has the amplitude, and this is how it looks, and this is the frequency of the signal. Based on those observed parameter for individual signal from individual supermassive black hole binary, you can try to estimate, let's say, the distance to the source or mass of the source. It will be possible for individual sources, but not in the case of gravitational wave background.
Okay, all right, thank you.
Hello, Dr. Prerna. Yeah, it was a wonderful talk. So I had a couple of questions. So how do you exactly calculate the energy released in a black hole merger event using the LIGO, using the PTA data? Like, is it something like comparing the data with the theoretical templates and calculate the energy?
Yes, exactly how it is. Well, I have not directly worked on it, but my understanding says the same. So I have shown here, right? So this is the signal you see, and this is the template. Okay. From here, what you know is the amplitude. You know the frequency. From here, you can estimate the mass. You can also estimate the total energy released of the system, which is, as I had also mentioned here, that the difference of the mass itself is telling you that around energy equivalent to 3 times mass of the sun is being released. So that's how you see. But So this is the total energy that you know of emitted in form of the gravitational waves.
Okay, so like, do we like to verify this? Can you use like gamma ray or high energy data to verify this
It's a very good
calculated
question.
energy?
See, so this particular event was a merger of two black holes, right? And you might have heard that there is no emission of electromagnetic waves coming out of black holes. So from a black hole merger, you will not see any gamma ray or X-ray or any other electromagnetic waves. But there was also discovery of neutron star merger, again by LIGO. This was very recent. And what they saw there, when the two neutron star merged together, they formed another body. And just after that merger, very close to when the merger was happening, they saw a gamma ray burst. Okay, and they observed it using the Fermi telescope. And yes, they had actually done the gamma ray observation there. So that will be specific to neutron star merger, but not in the case of black hole mergers.
Okay. Another question, like how does the pulsar waves gets affected by the various components of ISM? Like in ISM, we have warm or cold neutron medium. So how does the waves gets affected by that? And second question is like you mentioned about gamma ray factor. So like can you repeat like what exactly does it signify?
Okay, the second one is related to neutron star merger.
No, gamma ray factor. You mentioned something about gamma ray factor, 13/3, I guess.
Oh, gamma spectral index. Okay.
Yeah, gamma spectral index, my bad.
Sure. So I think this is what you're talking about, right? So see, what is this? This is my power spectrum. Okay, and this is proportional to the square of this characteristic strain which I was talking about. So this comes from theory, okay, and this whole derivation comes from GR. But the main thing to notice here is you have amplitude square, and then you have F. F is the gravitational wave frequency. You can easily see that you're going to have, since it is square, so you're going to have 2 alpha. Okay, so that's where this 2 alpha is coming from, because it's hc square. There is another factor of 3 here, which is coming. It's basically it comes from the definition of characteristic strain itself. What is characteristic strain? This is a strain theoretically defined in a way that when you are measuring a strain, which is, as I told, is delta L by L, right? So that is the strain that you measure. And when you measure that, that contains the effect of gravitational waves of the whole signal that LIGO saw. And that signal, as I showed you, had effect of all the frequency, which was varying from 30 hertz to 500 hertz. So that the strain that I am measuring has effect of all these frequencies. But to basically, since you are integrating, I mean, in the calculation you integrate over that frequency, you want to make sure that you take care of that effect. And mathematically, this characteristic strain is defined to take care of that effect. So once you do that calculation, you will see that there's another factor of 3 comes in. So it is because of this that your this spectrum is having 3 minus 2 alpha dependence, 2 alpha coming from the square and 3 coming from that definition of characteristic strain itself. So once you just put alpha equal to 2 by 3, where 2 by 3 is expected for the supermassive black hole binary mergers circulating in this circular kind of orbits. So that also comes from theory. Once you put that 2 by 3 here, what you get is 13 by 3. That's how this comes.
Okay. Yeah,
what was
that
the
makes
other
sense.
question?
Like in ISM, we have the cold neutral medium and the warm neutral medium. So in the DM factor that you have mentioned, So does it takes account of that, or like how exactly the pulsar waves gets affected by the CNM and the WNM in the ISA?
So I think in this calculation, the assumption is that ISM is cold. Okay.
Mm-hmm.
And to think physically, I mean, the way I imagine is that, okay, there are electrons in the way of these electromagnetic waves. It's going to
Mm-hmm.
scatter it around. It's like if I'm in a crowd and I need to scatter from many, many people to reach my destination. So I'm going to take more time to reach my destination if this whole ISM medium or of this whole crowd was not there. So that's the main concept behind it, and it is dependent on the radio frequency itself at which the pulse is emitted.
Okay. And you must have heard about the crab pulsar. So in the light curve of crab pulsar, it has got two peaks. So can we have those two peaks can be from the huge gravitational effects that is surrounding the neutron star. So that can result in the like we can see both the poles of the neutron star, you can say, due to the huge gravitational effect. But in the case of millisecond pulsar, do we have those do we observe two peaks in the light curve of any, like have you come across any millisecond pulsar
Definitely.
that have
Yes,
two peaks?
so I can tell you that one of our pulsar, so this pulsar 0437 and 2124, they have very
Mm-hmm.
complicated profile. They are not very easy profiles, and 2124 especially have very nice two peaks. Okay,
Mm-hmm.
and specifically you're talking about crab pulsar. Right? Crab pulsar is not a millisecond pulsar, so the spin of the crab pulsar is changing very fast. So which means the period derivative of the crab pulsar is higher than the period derivative of millisecond pulsar. So it's not very stable. That's why we don't use it for PT analysis. Okay.
Mm-hmm.
We need, as I had mentioned multiple times, what we need is stable, um, stable integrated pulse profile shape. And this is directly related to the rotation period of the pulsar itself. So if the rotation period itself is varying very fast, then my
Mm-hmm.
pulse profile will not be stable. So hence we cannot use crab pulsar to do PTA. But I think your question was something else. You
Yeah,
are saying that if you are seeing two peaks, is that related
yeah,
to gravitational waves? Is that you're asking?
yeah, if you are seeing two peaks, then what does it tells about the pulsar itself?
Hmm.
Like,
So what? How I understand is that, see, what you're seeing is these radio
mm,
pulse beam passing through the line of sight, right? Now, let's say this beam, this cone, which is as you see in this picture also, if it has a
mm,
complicated structure, okay,
yeah,
okay, this complicated structure of the beam itself is going to give you uh, uh, two peaks, not just one.
yeah, yeah, that makes sense.
Yeah.
On my final query, like how these results are gonna help in the mysteries of dark matter and energy.
That's a very good question. So, I'm not expert on dark matter, so I can't say much. But what I had read recently is that there's something called ultralight dark matter, and which are expected to change the gravitational potential of the galaxy itself, and somehow they are related to nano-gravitational waves. There are studies based on these results which are seen by pulsar timing arrays, but I can speak for specifically EPTA and InPTA results. There was a paper where they were trying to see which scenario, whether it is supermassive black hole merger, whether it is dark matter, whether it is gravitational wave from early universe, and so on. Which of these scenarios is fitting the observations well? And among those scenarios, they argued that they did not see any expected signal from ultralight dark matter. So that was ruled out. And the most favored scenario was actually the merger of supermassive black hole binaries.
Okay. Yeah. Thank you, Dr. Prerna. It was a wonderful talk. Thank you.
Ma'am, and a final question. A few minutes before you have mentioned that the mergers of the black holes doesn't produce any electromagnetic wave, right? But doesn't it produce relativistic jets?
Hmm. So, see, now it comes to why do we really see relativistic jets, right? So, relativistic jets are related to the matter the black hole is accreting around it. Okay, so black hole is there, and it's accreting matter. Okay, from its surrounding, and that accreting matter, uh, because of certain phenomena, that gets launched into jets. It's not something that's coming from inside of the black hole. Okay, uh, what I spoke about was the kind of signal LIGO saw. It was merger of two small black holes, uh, which usually the smaller black holes, unless they are in a binary system. Binary system means there are something called X-ray binaries also, black hole X-ray binaries, where there is a small black hole, stellar mass black hole, and there is some other star around it, like very similar to like our own sun. Sun is also a star. So this black hole is accreting mass from this star, and now matter is coming from the star, and that can get launched into jets. But if there is individual black hole sitting somewhere, other black hole sitting somewhere, not having any matter around it, not having any accretion disk around it, then you don't expect any jets. Then you just expect the two black holes merging. In that case, you don't expect any jets coming out of it. So jets, the source of jets, you need to understand the source of jet is through the accretion of matter, and that matter is coming from something else. That matter is coming from another star. That matter is coming from the surrounding of the supermassive black hole. So,
Oh,
if in the
okay,
case
ma'am.
of supermassive black hole, yes, you might expect something like that. When the merger happens, and if the jets are also interacting with each other, then you might see something. And there are certain studies, actually using GMRT also, where they see that where they have um,
AGNs.
agents. They talk about dual agents,
Uh,
and dual agents means there are two agents, and then the jets of these two agents are interacting with each other, and you see some specific kind of shape of these two jets when they're interacting. So that's one example of dual agents. One of my friend from my PhD days, she had worked on that. So yes, in those cases it's possible, but to understand the source of jet is not black hole itself. The source of jet is the matter which is being accreted from some other star or some other surrounding around the black hole.
Ma'am, and you have mentioned that the three solar masses from the merger would be converted into gravitational waves, which was detected by LIGO, right? And won't it be any other, energy conversion? Exactly, will it be converted into gravitational waves, or how can it? I mean, I can't quite get the part.
Hmm. Well, that's the okay. I mean, I am not sure whether I really have answer of that. Um, so from these observation, what they say that okay, from this template that they had produced, right, for the signal, this is the template that they produced. This template corresponds to a certain initial masses, and it also corresponds to certain final mass. And if you have really seen a gravitational wave, it's expected to it has certain amplitude, and I think this amplitude will tell you about the has the information of the energy being emitted as a form of gravitational wave. So that should I think tell us about the mass conversion into gravitational wave energy. So I think this information is contained within this template itself. That's how I understand it.
Okay, ma'am. Thank you.
Uh, I had a question. Uh, would is it possible to perhaps develop on this? It's an outlandish idea, but is it possible to develop on this idea of pulsar timing arrays to perhaps resolve and form an image with the gravitational wave data, like we do for light or sound.
I'm not sure if I understood the question. You're talking about imaging.
Yes.
Um, hmm.
Like like currently, my understanding is that using individual detectors like LIGO, you need extremely large baselines and have them like almost light years apart to try to image them. But uh, would it be possible to maybe use a different technique like pulsar timing arrays to sort of construct an image?
Um, there are two things. Are you talking about imaging the source itself, or you're talking about localizing the source in the sky? Because like it's like I want to know this is where source is. This is where the gravitational wave is coming from. Which one of the two you're talking about?
I was thinking something similar to how we have the image of the cosmic microwave background. We have a photo mapping out where how intense it is.
So then it comes to what you are really measuring. In CMB, what you're measuring is the sky temperature, right? So,
Yeah.
and then you measure it and you see, okay, if it is isotropic or anisotropic, right?
Hmm.
In gravitational wave background specifically, actually there are hints that there may be an isotropy in the background. So it's a background, okay?
Hmm.
And gravitational wave is not something that you see from eyes, so it's difficult to really imagine. But um, you can just imagine it like the example I gave, that water surface. But um, there is there may be a hint of anisotropy also. Why I'm saying this, because in the Parkes Pulsar Timing Array results, which I showed at last, this one, I don't have the plot here, but what they did, they had 18 years of data set. They used different slices of data sets, and using the different slices, they found what should be the amplitude of gravitational wave background, and they found that that amplitude was different. It was varying with time, and if it is varying with time, that means something is changing. And now something interesting is that Parkes Pulsar Timing Array make use of Parkes telescope, which is in southern hemisphere of Earth. So it means that Parkes telescope only sees southern pulsars. So it's only looking at the southern sky, and other PTs are looking at the northern sky. So it means we are finding something else. They are finding something else, which means the gravitational wave background is not really isotropic. It may be there may be an isotropy there. So that kind of understanding, that kind of searches will be done, and try to understand if there are anisotropies in the background or not. But imaging, I'm not able to really imagine that.
Okay. Okay. Got it. Um, and if there are any other questions? Okay, I think there are no other questions. I think this might be a great place to end the talk. Thank you for the wonderful and informative talk, ma'am. This was extremely informative, and I'm sure all the audience learned a lot from it.
Thank you very much. Thanks for the invitation. It was my pleasure. Bye bye.